Hello, we're going to look at some situations where we can describe SVA properties which at first glance look like sensible things to write, but surprisingly they can never fail. So this is not a fault of the tool will actually warn you, but the purpose of this is to show you if you don't understand why these things fail and overlook these warnings, you're going to have results that are bogus. So it's important you understand why, and it's important that you don't ignore warnings from the tool. So let's take a look at this small contrived example. We have a module here with inputs clock, reset, A and B, and output regs C and D. C and D are both driven to 0 at reset, and in the else branch here we have an assignment to C which is basically A delayed by 1 clock. And notice we haven't made any assignment to D, so D can only ever be 0, the value it's given at reset. If our initial condition is reset, of course. So we have a default clock here, which is a positive clock, and these two assertions we have here. So given that we're expecting D never to be 1, if we wrote an assertion that said if C occurs, this implies that we have a delay of 0 to an infinite number of cycles followed by D, we might be expecting that to fail. In addition, we've got another liveness kind of property here, that if A occurs, then the next cycle I observe C occurring not necessarily consecutive, that's what this equal operators means, between 1 and an infinite number of times followed by D. So being as D can never be true, if our initial condition is reset, then we may expect the tool to show these fail. However, if we did run those in the tool, what we find is that the assertions pass. And the left hand side of the implication, this precondition here, this is an automated cover which will automatically generate a cover for the left hand side of this implication, so it will check that C can occur, check that D can occur, they both pass. So why is this then? Well, the basic reason for this we can find if we look at the messages here. So it's saying we have a weakly embedded unbound sequence. So what does weak mean? Weak means an assertion or a sequence which is not required to complete. And what happened in the language reference manual is in 2005 the concept of strong and weak did not exist. Therefore, if we'd have compiled this using the 2005 LRM, we would have found the failures. However, being as what we're compiling with is this command here, -SV09 means compile with the 2009 language reference manual. If we put SV12, it means the 2012 LRM, and if we put nothing, that means the first LRM for System Verilog, which was 05. So if we were to change that, and I'd advise you to forget this immediately, if we were to change that, that would kind of get rid of our problem. We would see those assertions fail, but let's keep that there for the moment. So we're going to compile this, and the 2009 LRM, the default for properties is weak, and in the 2005 LRM, the default is strong, which leads to this different behavior, which is incompatible between the two language reference manuals. So what's a better way of fixing it rather than relying upon some TCL command? Well, you can actually do it in code, and this will be the recommended way. So what we can do is we can make the sequence on the right hand side of implication a strong one by using the keyword strong. So we'll just surround that sequence on the right hand side in brackets, and we will type out, and literally the keyword is the word strong. So this says now that this sequence must complete, meaning there is a requirement for D to occur, which there was not previously. So now, once we've changed that, if we were to now rerun that, what we see is these assertions now fail as expected, and that warning is just there from the previous time. That's not the new warning. We've re-invoked that script again. That warning did not appear. To summarize the cause of that problem is whether a sequence is evaluated as strong or weak, and that changed between the 2005 and the 2009 LRM. So the 2009 and 2012 LRM behave the same. So what I'd recommend you do is not play around with the -SV switch. I recommend you actually use the keyword to indicate to anyone reading this and the tool what your real intention is. So let's take a look at the second and final example, which has two properties in there. So we've got a simple module with a clock and a reset and two inputs, A and B, and an output reg C. And also internally, we've got some internal signals here. These bottom two here are flags which indicate whether we're on the first cycle or whether we're past the first cycle. So this first cycle flag is set in reset, and at the first clock thereafter, that flag is cleared. At the first cycle, we will sample this first cycle being true because it's set in reset as we just stated, and then we set that flag, and there's no way that flag can be any other value. So this flag after first cycle starts off as 0. If that after first cycle flag is true, which it will be sampled on the second clock out of reset, then we set this cint value to 0, and if either of the flags are true, then we drive the output C to be A and B. The output is set to 0 in reset. So C is driven to a 0 in reset. So that seems fairly simple, and what we've got here is a default clocking of pos edge clock, and we've got two properties which are very similar. So obviously they have different names, but what they're saying is that if after first cycle is true, which it will be from the second cycle and all future cycles after that, in the cycle that follows it, not C is true for this one, and C is true for this one. So surely we think to ourselves, then it can't be the case that both of these pass. Either one or both of them actually fail. There is a counterexample for both of those. So what may surprise us is when we look in the tool, we see that both of these properties actually pass. And the cover, the related cover, which is the automated cover of the left-hand side of implication, known as a precondition, that cover tells us that it is possible for that value to be 1. So we might ask ourselves, how can that be? The reason for this is because of this assumption here. So what this assumption says is always this internal net cint should be true. And we know that after the second clock, once we've sampled at the second clock this flag being true, then we're trying to drive this to a 0. Clearly that contradicts the constraints which the formal tool will never allow. Therefore, that represents the end of state space. So a very essential thing to think of when you're thinking of looking at the result from a formal proof is that all that pass means, or proven, is absence of a counterexample. In this case, it's impossible to produce a counterexample because the design is trying to do a different thing from what this assumption says. So the tool will go no further. So where we would actually get this failure demonstrated on at least one of these things is state space that gets excluded from the proof. Okay, so look in the tool. Is there any indication of the fact that we have a problem here? There is a command called sanity check. This is this command down here. That will reveal things like clock's not set up correctly and so on. But in this case, it doesn't detect a problem. So it appears that our automatically created covers pass and our assertions pass. So how we find this kind of problem is by writing user-defined cover statements. One of the covers we would probably have, checking that we can get C occur on the 5th cycle. That would demonstrate that we have a problem with overconstraining. The basic message of all these problems we've seen so far is 1. Don't ignore warnings. So remember we had that warning that indicated to us that we had a property defined which was weakly embedded. So remember, use that keyword strong if you intend that you're defining a liveness insertion and you intend the whole sequence requires to complete. And overconstraining is something that you will detect by your user-defined cover statement. So the tool is just following the instructions you've given. So when you say this assumption down here, the tool doesn't know whether you intended to do that or not. If you were to exclude the state space on the very first cycle, so let's say that this assumption instead said not cint, what we will find if we rerun the tool is the tool will tell us this because it recognizes that clearly it doesn't make sense to have 0 state space, because what we're requiring is, and this is what you see here, error, and it will tell us if we click that thing. And we look down here, we can see the assumptions over constrain at cycle 1. So check assumptions is the command to use, as it said there. Okay, and there we can see at cycle 1 we have a problem. So if we were to remove that, put it back as we had it before, let's rerun this again. So all appears well at that. So the task is inconsistent cycle 3. It's telling us a counterexample with 3 cycles was fine for this property, no conflict and no dead end. So these two things here, this is telling us that we have assumptions which are excluding state space on cycle 3, which is again what we understood when we went through the code. So notice I'm doing that command now has just added this property to me. So as well as that, user-defined cover statements would also have found that kind of problem, and it's essential that you always write these user-defined cover statements in order to detect overconstraining situations such as this. That concludes this video now, so thanks for listening and goodbye.